Welcome to a massive open online course on fluidization engineering. So, today's lecture on mass transfer in fluidized bed in gas, liquid and solid system. So, in the previous lecture we have discussed about the mass transfer phenomena in case of gas solid fluidized bed system. So, there we have seen that mass transfer mechanism or mass extent of mass transfer or rate of mass transfer depends on different factors like flow rate and particle size and also the physical properties of the system. And also they are whether the particles are porous or non-porous, and if the particles are absorbing the gaseous components, they are on its surface or not. So, based on which that mass transfer characteristics will be changing based on that particle characteristics. Not only that, in case of bubbling fluidized bed, that we have seen that due to the solid movement surrounding the bubbles and also the region of cloud surrounding the bubbles, that may govern the mass transfer there, and it is seen that interchange of that gas will give you the extent of mass transfer inside the gas solid fluidized bed. And here in this lecture we will see that whether that mechanism will be there or not, and or if gas liquid both will be there in presence of solid, then how that mass transfer will be happening here. So, here instead of 2 phase we will be considering that 3 phase, and then you will see that interface between this gas liquid and liquid solid, even gas solids will be there, and through which that mass transfer may happen. In this case, the mass transfer phenomena will be depending on the phase characteristics as well as the hold up of the phases inside the bed, and what is that mixing characteristics of the phases inside the fluidized bed. Now, of course, you will see that this will be the determining factor for the average conversion rates in fluidized bed, and then that conversion determines the performance of the fluidized bed reactor with different operating variables. And in the 3-phase solid 3-phase fluidized bed reactor, the solid phase can be used in such a way that whether this solids will be porous or non-porous, that depending on which the mass transfer enhancement may possible because of there will be some adsorbing phenomena of the solid particles there. Of course, the main important factor whatever we have discussed earlier also before starting this mass transfer phenomena inside the fluidized bed of this phenomena, that any reactor, whenever you are judging the performance of the reactor, you have to know the hydrodynamics characteristics of that particular phases, whatever flows of that phases inside the bed is happened. So, hydrodynamics of the phase basically mixing characteristics, flow pattern that change that mass transfer rate inside the fluidized bed. We know that mechanism of that 2-phase theory of mass transfer characteristics there. So, here you see, if you see that the reaction that equation 1 here, one mechanism, that what does it mean, that J A that will be equal to C A G bar by 1 by K G A plus 1 by M into K L A E A plus 1 by M K S AP plus 1 by MK double dash R AP. What does it mean actually this? Why we should write this equation there in fluidized bed for 3-phase operation for mass transfer mechanism. Of course, it is the things that if you are considering the component A is transferring from one phase to another phase, then you can say what should be that rate of mass transfer there. So, if we consider that rate of mass transfer is at Z A into A, then it will be is equal to what, like this. Of course, whenever transferring component A from one phase to another phase, there will be certain resistance to transfer from one phase to another phase. Now, what are those resistance here? These resistances are represented by this R1, R2, R3 and R4. What is this R1? R1 is that is 1 by kGa. This 1 by kGa denotes the resistance to mass transfer in the gaseous phase here, and R2 is 1 by mKLA Ea, the resistance here to mass transfer in the liquid phase at the gas liquid interface. So, here gas to gas liquid interface, and then what is then 1 by mKSAP, the resistance to mass transfer in the liquid phase at the liquid solid interface. So, first here gas to liquid, then liquid to solid. So, there will be interface between liquid solid here also, and then R4 another resistance, it is called the resistance to reaction at the external catalyst surface there. So, we are aware of the resistance of the mass transfer whenever the component is transferring from one phase to another phase, like from gas phase to the solid phase here. So, what are those barrier or resistance that the cross that is called here? One is gas to liquid interface, and then liquid to solid interface, and then solid phase there. So, initially it will come from gas phase, like if it is suppose this gas phase, and then gas phase to the here liquid phase, and then this is liquid phase to then it will go to the solid phase there, and then it will be there the remaining part. Again it will be the gas phase or solid phase like this. So, there may be a barrier of that gas liquid solid interface there. So, this mass transfer rate JAA can be represented by this resistance in terms of resistance, that is called CAG by this is one that is called by R1 plus R2 plus R3 plus R4. So, in this way this mass transfer rate can be expressed in case of 3-phase fluidized bed system, and here in this case CAG bar is the constant concentration of the component A in the gas phase throughout the reactor, and R1, R2, R3 and R4 are the so called resistances that control the overall conversion rate, and the model used here shows the all resistance in series here, because it will come as R1 plus R2 plus R3 whenever their mass transfer from the gaseous phase to the other phases through their interfaces. For a first order reaction, you will see that generally in case of porous particles, and some specific example for that, the first order reaction, then R dash that is R4 should be replaced by that R dash 4 here. Here this R dash 4 will be represented by this equation dP by 6 MAP di phi into tan H phi here. This phi is called this Thiele modulus, which will be depending on that particle size and also rate of reaction there inside the bed. Also there will be surface area of the surface and molecular diffusivity of the component I. So, in this case this for first order reaction you will see that this R4 that this resistance will be represented by in terms of particle diameter and Thiele modulus. So, from this I think rate of mass transfer you will be able to know what extent of mass transfer in the fluidized bed for 3 phase system is going on. And there is the mechanism, that means here all the phases whenever it will be crossing, then there will be some resistance there, liquid phase, gas phase, and gas liquid, solid liquid, and the solid phase resistance will be there. See this picture here, this is a well known profile of concentration at the bulk and the interface whenever there will be mass transfer inside the gas, liquid, solid systems. So, in this case you will see that here if we see that this concentration profile, this is the gas bulk phase. In this case the concentration will be almost remain constant, and after that you will see in the very adjacent to that interfaces of that gas liquid, that means very thin film of the gas between this liquid and gas, then there will be a certain change of concentration here, it will decrease, and at the interface there will be a certain concentration, and at the interface there will be some equilibrium of that concentration of gas to the liquid here in the liquid. So, here it will be the liquid concentration and gas concentration, it will be at equilibrium condition here, that will be related some equilibrium constant. And after that you will see whenever it will move to the liquid and very adjacent to this gas liquid interface, very thin film of liquid, whenever it will pass through this thin film, then here again the concentration will decreases because resistance is high, and then after that in the liquid phase there will be a constant concentration their profile for that component A. Again if we consider that solid phase here, that here liquid solid interface, in this case you will see that at the solid surface there will be reaction surface, and adjacent to this solid surface that is liquid solid interface, there will be thin film, that concentration will be decreasing, and then here again at the surface, the solid surface, there will be a reaction will take place there. So, this is the profile, concentration profile when the component will be reacting with some other reactant and how the mass transfer is happened in the fluidized bed there. And another profile here, if suppose there is a porous catalyst is used, then what will happen, this at the solid surface, this solid surface the concentration profile will be exponentially decreasing with the that means thickness from the surface to the solid. So, this mechanism or concentration profile is shown first by Binekers and Van Schwijs 1993. So, from this mechanism we can infer what should be the actually mass transfer mechanism and what should be the concentration of the component A, which is transferring from one phase to another phase by changing its concentration from its phase layer to the another phase. Now, if porous particle mass transport and reaction if there are parallel, then overall the process can still be described by the resistance in series. So, from these resistances in series that R2 might be influenced by the presence of all particles in several ways. So, the specific gas liquid interfacial area A that can be changed by the presence of the particles there. Of course, whenever you are going to do any experiment in gas, liquid, solid, fluidized bed, suppose in a column from the bottom if you supply some gas, then what will happen in solid liquid slurry, then you will see there will be a gas liquid solid operation, and there will be some hold up of gas inside the bed, and then this hold up of gas will be changing with the particle concentration and also size of the particles, and then the interfacial area, gas liquid interfacial area will be changing in presence of solid particles there, and because of which you will see that mass transfer rate will be changing, because the mass transfer rate that depends on the interfacial area of gas liquid as well as gas solid. So, in that case individual mass transfer coefficient in liquid itself can be influenced by the presence of particles, even if these are inert in nature. In the case of dissolving particles, you will see even the solubility of gas phase component may change due to the products, but generally the effects of solubility is negligible. So, very interesting that the mass transfer rate depends on that interfacial area of gas and liquid, and also solid and liquid surface area. So, in 3-phase fluidized bed you can control or you can change the gas hold up, and because of which that interfacial area of gas and liquid, and because of which that rate of mass transfer will change in the fluidized bed. Now, how can I then enhance the mass transfer in the presence of particles? So, now, enhancement of mass transfer can be defined first here by equation 4, that is given by Binekers and Vanch was 1986, that it is defined as that what will be the mass transfer with particles and what will be the mass transfer with the same, but it will be with inert particles, in which is evaluated at the same overall driving force of concentration. Inert means that neither the particles nor components produced from the particles which are participating in the reaction as a reactant or a catalyst there. And also you will see that inert particles do not adsorb the gas phase component, that is transported towards the bulk of the slurry, nor any other reactant or reaction product there. So, basically what would be the enhancement of this mass transfer that can be calculated by knowing the mass transfer with particles and mass transfer with the same, but inert particles there inside the bed. Whenever we are talking about the mass transfer rate inside the fluidized bed, we have to know what should be that rate and how it depends on. Of course, from the basic we know already, we have discussed earlier also that the mass transfer rate that depends on concentration differences, that is called driving force, and also that cross sectional area, or you can say that surface area of the interfaces there. So, if we consider that if this mass transfer is proportional to that concentration difference or driving force, then what should be that proportionality constant? That proportionality constant can be represented by the mass transfer coefficient. Now, this mass transfer coefficient, sometimes this whenever you are considering that mass transfer, that concentration difference in the liquid phase, then it will be liquid side mass transfer coefficient at the gas gas liquid interface here, and if you are considering the gas side, then there will be a gas side mass transfer coefficient. Generally, it is very easy to estimate the concentration of that component which is transferred in the liquid phase, and so liquid phase mass transfer is very interesting. And another important point that sometimes for individual phases it is very difficult to calculate that what is that for specific surface area for that individual what is that for unit surface what should be the mass transfer coefficient, then what should be the overall mass transfer coefficient for the whole reactor, and it is actually calculated or estimated by some chemical method or physical method there. And both this method, physical method or chemical method is described in the books in Majumdar in 2016 that in details, and for further reading we are just suggesting that okay, this can be followed for mass transfer phenomena, how chemically or that physically can be estimated. And for low solids concentration, one may assume that the solids do not affect the value of mass transfer coefficient, that is the overall mass transfer coefficient, so that the existing relations of two phase gas liquid reactors can be applied there. So, volumetric liquid side mass transfer coefficient at the gas liquid interface KLA that can be calculated by absorption theory or by any chemical theory with or without reactions there. Now, if we change the system's properties inside the fluidized bed, then what will be the rate of mass transfer? Is there any change, or whether it should be enhanced or lowered the mass transfer rate there inside the bed? Of course, viscosity of the fluidized bed or fluidizing system, they are very important because the resistance of the mass transfer that depends on the physical properties of the system. So, if the density difference between the solids and the liquid is small, or if the liquid viscosity is very high, then you can say slurry, that means liquid solid mixture, behaves as a pseudo homogeneous phase, and you can say that relations for that overall mass transfer coefficient as a function of the effective suspension viscosity and it can be actually expressed by correlating with that viscosity. Of course, it is based on the experimental data, how we cannot actually predict this by mechanistic way or from the what is that that is called that material balance or some basic principal equations. It is not possible, but from the experimental data by empirical correlations that you can correlate how this mass transfer coefficient will be changing with the viscosity. So, Osterich and Schumpe here 1987 they have suggested one correlations of mass transfer coefficient which will be relative to the mass transfer coefficient of that means without solid and how it will be changing in presence of solids and if you add some solid particles, then of course, the slurry viscosity will be changing. As per Einstein theory, that you know that if you increase the solid concentration in the liquid, then the viscosity of the slurry will increase. So, according to that, if you add some solid particles, there will be a change of viscosity and you will see that reduction of mass transfer will be there. So, if you do the experiment with and without solid particles, you will see that mass transfer coefficient will be that KLA by KL0 here, if you represent it by here this KLA in presence of solid and KLA 0 in presence without solid particles, then this this will be equals to that ratio of that effective mass effective viscosity of that slurry by the viscosity of the phase without solid, then to the power minus 0.42. So, it is seen that if in presence of solid particles, this mass transfer coefficient is decreasing exponentially with a power of 0.42. And this mu effective means effective viscosity. Why this effective viscosity? Effective viscosity means here you will see whenever you are adding solid particles with a certain concentration, and you will see there will be a change of viscosity inside the bed, and this change of viscosity, that is this slurry viscosity compared to that only clear liquid, that means pure liquid, only water viscosity, then it will be the effective viscosity there. So, this effective viscosity generally represented for the non-Newtonian behavior of fluid. Now, slurry generally behaves like a non-Newtonian fluid. So, that is why in that case here this effective viscosity will be represented by the shear rate here. So, this is directly proportional to that what is that shear rate here, shear rate to the power n minus 1 here to here k. So, this gamma effective dot, it is directly proportional to this velocity of the gas inside the gas liquid solid fluidized bed, where c is the constant, this c is constant is equal to 2800 meter inverse. Now, interesting that other conditions remain here identical. So, mu 0 is the viscosity of the pure liquid which is represented as mu L, and for u z less than 8 centimeter per second and effective viscosity between 0.5 and 100 millipascal second, then only you can apply this equation number 5 to predict the mass transfer or overall mass transfer coefficient in presence of solids. That is the effect of viscosity, how this viscosity, if you are changing, then how this overall mass transfer coefficient will change inside the bed. And if you are using that ionic aqueous solutions in the fluidized bed, then you will see that as per the bubble column reactor, then for the water and ionic aqueous solutions, and if you are using that Kieselguhr with a small particles of 7 micrometer and also alumina or activated carbon of various fine particles like 8 micrometer or 5 micrometer particle size, in that case you will see that it is seen that viscosity, that is effective viscosity, because those are non-Newtonian fluid, this effective viscosity will be 2 times of that water viscosity there. So, in that case it is seen that for this ionic aqueous solutions, that the overall mass transfer coefficient in presence of these solid particles would be changing with exponentially with a coefficient of 0.39. And for gas velocity less than 8 centimeter per second and effective viscosity 1 to 100 millipascal second, and this mu effective and this shear rate, effective shear rate, those are related to this gas velocity, and then this proportionality constant with this gas velocity will be represented by this C, and which will be equals to 2800, that already been considered earlier. And here important point is that this K is called that fluid consistency index, that as per non-Newtonian fluid behavior it is expressed. Now, if is there any non-wettable particle there inside or not. So, non-wettable particles may reduce the value of overall mass transfer coefficient there. So, for non-wettable particles in aqueous solutions, the extra decrease could be described by assuming surface blocking of the gas liquid interface by Langmuir, you can say that Hinsel-Wood type of adsorption of the non-wettable particle according to this equation 9 here. So, here this is alpha is called that fraction of the interface that will be covered by the particles, and k dash is generally the constants. It is taken or it can be observed experimentally will be equals to 9 for polypropylene, that is given by Shumpe et al. 1987, whereas this k dash may increase with the gas liquid solid contact angle, and this k dash is equal to 9 for theta is equal to 120 and k dash is equal to 6 for theta is equal to 96 degree. So, in that case we can have that if there is any wettable particles or non-wettable particles, how this mass transfer rate will be changing there. So, it is seen that that mass transfer coefficient may decrease if there is a non-wettable particles are used there inside the bed. Now, effect of solids and gas fraction. Now, very interesting that for 3-phase fluidized bed you will see that how much solids are being used for that mass transfer operation, that is very important. So, fraction of the solid inside the bed, that is very important. So, that depends that affects that mass transfer coefficient there. So, mass transfer coefficient to be reduced by the presence of solids, although this reduction is less pronounced in the Chern turbulent condition of the fluidized bed system. So, equation 10 can be used to calculate the mass transfer coefficient with a certain concentration of the solid fraction inside the bed within a gas velocity less than 8 centimeter per second, and the column diameter is less than 9.5 centimeter. Now, according to Contd et al. 1984, they have suggested their own correlations from their own experimental observations, and they have developed one correlations in terms of Froude number, Reynolds number, and also you can say that there will be some other called this is called here NS, that is here this called transition number here. This turbulent flow regime, turbulent flow regimes, this numbers of this Froude and the Reynolds number will be changing because of the gas hold up, how it will be changing in this gas liquid solid fluidized based system. Now, you will see that heterogeneous Chern turbulent flow regimes, this gas hold up in presence of solids will be changing because of the change of viscosity whenever you are adding some solid inside the bed, and because of which you can get the change of mass transfer coefficient inside the bed. And then here see equation 11, how it is related. This epsilon G H is called that gas hold up at this heterogeneous Chern turbulent flow regimes, and this epsilon G H 0 is called that gas hold up at there will be no actually that Chern turbulent regime, that means here this laminar flow regime. So, in that case what should be the gas hold up, and how this gas hold up will change this mass transfer coefficient. Now, without actually changing any fluid velocity, then Reynolds number will be 0. So, in that case you will see that this part, this Reynolds number will be 0, that means here mass transfer coefficient will be in presence of solids will be 0 there. Whereas, in case of Froude number there, you will see that if I change this terminal velocity of the, that means this terminal velocity of the solid particles there without having any gas velocity, without having any liquid velocity, that means in the still gas liquid solid medium there, only solid particles will be just settling down with a terminal velocity. So, at that terminal velocity condition, what will happen? You have to change this what is that Reynolds number, that will be considered at here 0. So, in that case KLA will be equals to 0, but in this case if you are considered that there will be no flow, then you cannot here consider this Reynolds number. There will be a certain change of that means here that what is that Froude number here according to the definition of this Froude number. So, because of which there will be change of mass transfer coefficient. So, according to this equation 11, if we here do this Reynolds number is equal to 0, this part will be equal to what? Infinity, that means here ultimate it will be equal to this part, what should be the value here? 1 by n RE, 1 by n RE is equal to 1 n RE means here this is Reynolds number, if it is 0, then 1 by 0, that means infinity. So, here what does it mean? That means infinity here infinity, then 1 by 1 plus infinity, that means 0, that means 0 here. So, at a terminal velocity, at a certain terminal velocity, there will be a 0 mass transfer parallelly also. So, this is totally complex phenomena at this Chern turbulent condition they are. So, and you cannot apply this equation only for this heterogeneous Chern turbulent flow regimes. So, this equations is applied, total equation is applied for the transition regimes also. So, here Chern turbulent, heterogeneous Chern turbulent and the transition regime that is just entering to that heterogeneous Chern turbulent flow regimes. So, in that conditions all those portion will be included here. So, this is basically the empirical correlations, not like that you will get the directly the just substitution of this what is that parameter here, you will get directly that equation. So, there will be certain range of applicability of this equation and for which you will be able to calculate. So, you cannot consider here that Reynolds number to be equal to 0, so that mass transfer will be equal to infinity, that is also not possible here. So, there will be a certain range of applicability of this correlation, and this here NS is very interesting, that this NS will give you that what the system properties. You will see that if is there any surface tension change inside the bed or not. If you are adding some surfactant, of course, there will be surface tension will change. So, accordingly that mass transfer coefficient also will change. So, that will give you the variation by changing this NS here. Now, according to Sun et al. 1988, they have given another equations to actually predict the mass transfer coefficient in gas liquid solid systems. So, they have given what should be the effective viscosity of the suspension, and what would be the concentration of the solid, and what should be the you can say that effective you can say it is called that kinematic viscosity of the fluid inside the bed. So, that will affect that overall mass transfer coefficient here. So, this empirical correlation of equation 17 also will be used to calculate the mass transfer coefficient in terms of what is that concentration of the solid, what is that kinematic viscosity of the suspension, gas velocity, and this effective kinematic viscosity of the fluid can be calculated by this equation number 18. And here this N3, N2 and N1, all those are coefficients that can be obtained from this what is that from this table. This data are given here. Now, mass transfer coefficient in bioslurry fluidized bed, what is that? Now, bioreactors containing that you know that you can do that experiment with free bacteria in aqueous media, bacteria in aqueous media can be considered as a slurry here, with the cell being very small and having a density close to the aqueous medium. One may expect the concept of a pseudo homogeneous liquid phase to be that will be successful, and often you can see that this biophase behaves as a non-Newtonian liquid inside the fluid, and if you are changing this fluid properties by adding this bacteria, that means slurry concentration will change, other properties of the fluid also will change, and because of which you can see that the change of mass transfer coefficient also will change. You can use that correlations previously whatever given there to predict the mass transfer coefficient or calculate the mass transfer coefficient inside the bed. Now, you will see that Kawase and Mu Young, they have done several experiment and they have suggested the same empirical correlations for the volumetric gas to bioslurry mass transfer, both for the case when the slurry is Bingham plastic and for the what is that cation fluids there. So, equation 22 can be used to calculate the mass transfer coefficient for that what is that Bingham plastic fluid, and they have done the experiment with this organisms, and there is slurries of these microorganisms that behave like that Bingham plastics fluids, and accordingly they developed this correlations 22 to represent the mass transfer coefficient. Here you will see some coefficients C and F. C can be taken as 500 meter to the power minus 1, and F should be equal to 1 minus beta to the power 1 by 4 for Bingham fluids, and F to be equal to 1 minus root over beta to the power half for a cation fluids, and this beta is nothing but the shear stress in the y direction to the shear stress, overall shear stress there. The volumetric gas side mass transfer coefficient, that is represented by Kga. Now, if you have that the gas whatever is being used that are sparingly soluble inside the bed, and it is not usually the rate controlling, and if you are using that it would be for very soluble gases, conversion may be complete whatever reactor design is selected, that due to the what is that large numerical values of KLa, making such processes extremely that fast. So, in that case selectivity is affected by the liquid concentrations of gaseous reactants, and which may give the accurate information of the mass transfer coefficient of gas, which can be vital for the designing of the processes, and of course, you will see that based on that possibility of any gas phase rate controlling effect, which can be excluded with the certain phenomena. And in this case, whenever you are considering that gas phase mass transfer coefficient, one important point is that suppose there is a gas liquid solid mass fluidized bed, and gas is distributed as a dispersed phase of bubbles, and then for first reactions the enhancement at the gas liquid interface here in this case bubble surface to the liquid interface, then in that case knowledge of the true gas liquid specific contact area, that is denoted by A, will be required, and that will give you the more actually information about the mass transfer coefficient of overall mass transfer coefficient. So, here A is the specific interfacial area. Now, if we produce more finer bubbles inside the fluidized bed, then you will see that you will get more interfacial area and then more overall mass transfer coefficient, and of course, more mass transfer rate there inside the bed. For small particles typically below 100 micrometer, 100 micrometer here, 100 micrometer, and a low solids hold up below 0.6 volume percent, then small particles may cover the bubble surface, thus prevailing the coalescence of the bubbles and resulting in smaller bubbles and on increased specific surface area. So, in that case the specific surface area will be represented by this equation number 27. Now, this specific interfacial area is depends on the what is that particle size. Now, if you are considering that gas phase to the liquid phase mass transfer, of course, you have to consider the bubble size there. Now, what is the bubble size, that is dB, that you have to first obtain by certain method, maybe the photographic method will be the useful one. Otherwise, you can consider other that PIV method and other you can say that conductivity probe method to calculate or to find out the bubble size. Once you know that bubble size, then what should be the interfacial area you can calculate. Now, for this you need further information about the gas hold up inside the bed. How to calculate that gas hold up, how to estimate that gas hold up, we have already discussed about this earlier also, that you can calculate this or you can estimate this gas hold up by phase isolation method, or you can estimate this gas hold up by what is that conductivity method, and there are other various several methods to find out this gas hold up method. And I think the phase isolation method is very easier to calculate for overall gas hold up. If you know that this overall gas hold up, then equation 27 will give you the interfacial area of the bubble there for taking part to calculate the or to estimate the mass transfer, overall mass transfer coefficient. And the effect of an increase in interfacial area is enhanced further by the fact that smaller bubbles have lower rising velocities, which lead to increasing gas hold ups with decreasing bubble diameter. Very interesting that of course, this hold up or bubble size depends on that physical properties of the system and also fluid flow inside the bed. Fluid flow sometimes change the kinetic energy and the momentum exchange between the phases, and because of which that there will be a breakup of bubbles or coalescence of bubbles, and there will be a net change of a bubble inside the bed will be there. Even you will see there will be a change of gas hold up because of those variables, and you will get the interfacial area. So, interfacial area depends on what that maybe that system properties, maybe that flow properties, maybe what is that the geometric variables also inside the bed. And an increase in solid content also may increase or decrease the gas liquid surface coverage, or you can say surface area in that case. So, an increase in solid content may increase the percentage of gas liquid surface area, suggesting an increase of interfacial area with solid content there. However, adding more fine particles typically above 0.6 volume percent, that may result in a decrease possibly because of extra particle that sometimes cannot find any uncovered bubble surface that is left, and also have to remain in the bulk. So, so that it contribute to the increase in effective viscosity of the slurry. So, in that case there may be change of specific interfacial area, and also increase in interfacial area will be more than a factor of 2 after adding of 0.3% of fines, that is stated by Sharma and Mashelkar 1968 there. And so now 1981 measured the influence of solids on both gas hold up and bubble size distribution, and they have developed correlations, respective correlations as given in equation 28 and 29. According to Smith's et al. 1987, for viscosity above 5 millipascal second, they have given that they have given correlations that for interfacial area, specific interfacial area in terms of solid concentration, or you can say solid fraction inside the bed as this here. Here A by A 0 is equal to 1 minus 3.3 into epsilon s minus 0.03. From this equation you can calculate what will be the specific interfacial area in presence of solid, if its fraction is some extent there. If it is less than, fraction is less than 0.03, then you can calculate from this equation. And A 0 is the specific interfacial area for is there no what is that solid fraction there inside the bed. And liquid side mass transfer coefficient at the gas liquid interface K L. Here this is very interesting that this K L is the individual mass transfer coefficient, not this overall mass transfer coefficient here. The influence of the presence of solids that are inert in any aspect with respect to the mass transferred component A here. Whereas, other cases you will see that under special circumstances the gas to liquid mass transfer rate of a component A that can be enhanced by the presence of particles because of the adsorption on what is that catalyst surfaces or the reaction with the particles at its surface. Now, in present in present of what is that, in presence of unreactive inert particles here, we can see that from the definition of what is that K L individual mass transfer coefficient, if we apply that film theory there, that K L should be equal to what is that dA by delta L. What is dA? dA is the diffusion coefficient and delta L is called the film thickness in the liquid side. And it follows that inert solids may affect this K L in two ways, and here way 1 and way 2 here. The presence of inert particles close to the interface may reduce the effective volume fraction of the liquid available for diffusion. By this K L can be reduced via a lowering of the effective diffusivity, that is dA. This effect can be significant only for particle diameters of the order of the film thickness for mass transfer delta L or even smaller. So, in this way you can calculate what should be the this individual mass transfer coefficient by this film theory. Otherwise, penetration theory also you can apply there to calculate this mass transfer individual mass transfer coefficient by equation 32 here, given this K L is equal to 2 into root over dA by phi T C here. So, in this case what will the exposure time of that what is that contact time of that gas solid or what is that liquid solid interface there, and that depends on. So, this is called that contact time T c. Now, this contact time, how to calculate that contact time, it will be discussed later on. So, another way that we have to discuss that the particles may influence the hydrodynamics close to the gas liquid interface, thus affecting KL via changing this film thickness and the contact time by this penetration theory. The influence of small heavy particles on the mass transfer coefficient in bubble columns relative to no solid present here, Shumpe et al. 1987, they have given these empirical correlations to calculate this mass transfer coefficients without solids there. So, based on this equation, you will be able to calculate what will be the individual mass transfer coefficients in presence of that means, if you know that solid fractions inside the bed. Now, for particles with densities close to the fluid density, such as are frequently found in bioreactors, the pseudo homogeneous liquid approach is often successful in this case. So, for such systems, Kawase and Mu Young 1990, they have developed one theoretical relationships for that individual mass transfer coefficient using the combination of Higgs penetration theory and the Einstein Lee periodic versus sublayer model to predict the contact time there. So, this contact time that depends on what very interesting that this contact time will be depending on the viscosity of the basic fluid and also the energy dissipation in the fluidized bed there. So, by this equation that is equation 34, you can use what should be the contact time for that. Now, assuming the contact time for mobile surfaces to be 1/4 of the viscous sublayer, then of course, bursting period for the immobile surfaces, they sometimes affect they are actually the surface exchange or you can say that surface mobility, and because of which that there will be some change of what is that mass transfer coefficient, and of course, the energy dissipation between energy dissipation during that what is that flow there, and this energy dissipation depends on that how what will be the rate of gas inside the fluidized bed, and that energy dissipation denoted by this E bar, that will be equal to U g into G. So, equation 35 can be used to calculate the individual mass transfer coefficient. This individual mass transfer coefficient then depends on this what are that here this density of the liquid, viscosity of the base liquid, and then what is the energy dissipation, and also the Schmidt number there. And this equation 35 is the general equation that can be used for Newtonian and non-Newtonian liquid, but for Newtonian liquid you have to consider that beta will be equals to 0. Now, case 2, under reactive conditions without requiring a priori knowledge of the kinetics there. So, in that case mass transfer coefficient at liquid solid surface can be expressed by this equation number 38. This equation 38 will give you the what is that mass transfer coefficient of that liquid solid interface. This NSHC, that means here Sherwood number is denoted by that Ks dp by d here. Ks is the what is that liquid solid interface mass transfer coefficient, dp is the particle diameter, and d this d is called the diffusivity coefficient or diffusion coefficient, and Schmidt number is defined as that mu L by rho L into d here. This C and N1 N2 are the constants that can be obtained from the experimental data. You can do one experiment and then find out the different results with different variables and make this equation and feed this equation with your experimental data and find out the coefficient C n1 and n2. And if you are considering the local turbulence inside the bed, then the mass transfer coefficient, of course, this liquid solid surface then of course, will be affected by this turbulence. Now, this turbulence can be considered by the Kolmogorov's theory for the local turbulence, and if you consider that Kolmogorov's theory of local isotropic turbulence, then it can be represented by this W by rho L V L, whereas this W is equal to phi V is into delta P. That means, there what should be the pressure drop inside the bed, and otherwise you can calculate it from that velocity of the gas and what is that viscous velocity of the gas and volume of the liquid inside the bed and the density of the liquid. And once you know this, then it will be very easy to calculate what should be the Reynolds number inside the bed based on this. And here one important coefficient is called C1, this parameter. This parameter will give you that what extent of mass transfer coefficient will be changing inside the bed. Now, if is there any wall effects inside the bed, then of course, the Reynolds number will be changing here by this equation 44, you can say. In this case, this the velocity of the liquid, that will be of course, that characterized by the turbulence velocity that is proportional to the liquid circulation velocity inside the bed. So, as Pandit Joshi they have given that theory that whenever liquid is moving inside the bed, even gas, liquid, solid also in a bubbling fluidized bed, there will be internal circulation there, and there will be change of liquid velocity. That circulation velocity of the fluid, that will give you the turbulence inside the bed. So, that turbulence velocity is proportional to the liquid circulation velocity inside the bed. That liquid that characteristics turbulence velocity can be represented by this equation number 45 as per Pandit and Joshi 1986. And in this case, the maximum possible value of this what is that liquid circulation velocity will be is equal to this V L dashed, which is given in equation number 46. So, once you know this what is that maximum possible value of the circulating velocity of liquid, then what should be the modified Reynolds number. Once you know this modified Reynolds number, and if you substitute this equation Reynolds number, equation for Reynolds number here in this equation earlier, that equation 38, if we substitute here, then we can get this modified in terms of modified Reynolds number, equation number 48. Then after that, you can find out what should be the Sherwood number, and for which you can calculate what should be the liquid solid mass transfer coefficient there in the bed. So, this equation 48 along with this 49 and 50, you can calculate what should be the mass transfer coefficient for liquid solid side. Now, this enhancement of the gas liquid mass transfer based on adsorption of solids particles. So, is there any adsorption happens in the on the solid particle surface, then how this enhancement of the gas liquid mass transfer happens there. So, different types of you will see that enhancement will be happened, that is in presence of sometimes particles will adsorb the transferred component only physically, sometimes particles catalyze a chemical reaction that will involve the adsorbed gas phase component. Sometimes particles in the mass transfer zone react with the transferred gas phase component. Sometimes particles in the mass transfer zone dissolve and the dissolved reactant reacts with the transferred gas phase component. And you will see most of the cases there will be a adsorption of the components on the surface of the solid particles. and reaction will be on the surface of the reactions. Other particles such as colloidal particles, emulsions, micelles etc., also may change the mass transfer rate inside the fluidized bed, and also you will see combination of all these possibilities may enhance the mass transfer inside the fluidized bed there. If particles absorb the transferred component only physically, then you can represent this mass transfer rate by this equation 51. In this case, Cs is the solid concentration and K Ad is the adsorption equilibrium constant here. So, if the adsorption is at equilibrium and the solids concentration is not excessively high, then bulk liquid phase concentration may be retained by this equation number 51. And the flux Ja in the bulk of slurry can then be expressed by this equation number 52. Here Ea is the enhancement factor due to the adsorption of A on the particles in the mass transfer zone, that is close to the gas liquid interface, and the subsequent desorption or redistribution of A in the bulk. And also you will see that it will be obvious that in order to obtain the enhancement, the particles should indeed grazing during their contact time in the mass transfer zone. And if you consider the adsorption of a gas phase component in a slurry with a relatively simple homogeneous model based on the Higgs by penetration theory, and if you neglect any gas phase resistance there. So, in that case you will see that there will be a certain linear adsorption relationship for the adsorption of the dissolved gas on the particles, and the concentration of the adsorbed component can be expressed by the equation number 53 here given. So, in this case this Na is the number of moles adsorbed on the particles, and Cas the concentration of A in the liquid at equilibrium condition and with equal concentration at the solid surface. And if we simplify this equation number 52 along with those equation 53 and 51, then we can say that equation number 54 can be obtained, and 55 and 56 will give you the overall what is that mass transfer coefficient for the particles inside the bed, and overall interfacial area for the particles there, and in terms of solid concentration. The differential equation for the penetration of gas A into a typical surface packet, that we have already discussed about that surface packet is there is any solid bulk of solids are behaving like that one, that is simple what is that bulk of solids that may change that mass transfer rate there, and in that case you will see for dissolved A, for adsorbed A, what should be the mass transfer rate, that can be expressed by this equation number 57 and 58 here. And the enhancement factor can be calculated based on that then by this equation number 59. In this case the contact time is the main important governing factor, that which will give you that which will give you that enhancement degree of enhancement of the mass transfer inside the bed, and this systems has been solved numerically, which is given by Holst-Vogt et al. 1988 to calculate the enhancement factor based on this contact time and also the change of concentration within a very short what is that film thickness. There are several asymptotic solutions also given for this equation number 59. Here equation 60 has given by Kars et al. 1979 based on instantaneous equilibrium between particles and their surrounding liquid, Here in this case, this enhancement factor directly related to this concentration of the solid, and also the what is the parameter, what is that mass transfer adsorption rate, that is Kp. And here other unknown parameters like equation 61 and 62, that will give you that degree of loading, that means they are inside the bed, and also determine the rate of adsorption and the enhancement, and represented by the Hutton number, that is HAH, this Hutton number, and that depends on the reaction kinetics also. So, that reaction kinetics will give you that if there is the Hutton number criteria is given by 63 is matching, then only you will be able to calculate at that particular condition what should be the enhancement factor inside the bed. And there are some other there are various other solutions given by different investigators. In this case, the enhanced gas absorption model given by Vinke 1992. I think it will be suggestive to follow this literature to get the enhanced gas absorption model to have this what is that mass transfer enhancement in the gas liquid solid fluidized bed based on the film theory. And based on that film theory, if their particles take part in a chemical reaction, Westard et al. 1984, they have given some equations based on that their experimental results, and also the enhancement in a slurry reactor in case of first order reaction, constant gas phase concentration and with no liquid through flow of bulk. Wimers and Fortuyn 1988, they have developed this equation number 73 here, and here this Hutton number is represented by this equation number 74. So, based on this you can calculate what will be the enhancement of the mass transfer in a slurry reactor in case of first order reaction. And for first order reaction at the porous catalyst surface, you can represent it by equation number 75, and with A dash pi the specific solid's external surface area at the gas liquid interface, it will be represented by this equation here 76 for this Thiele modulus. And once you know this Thiele modulus here, then what should be the mass transfer coefficients, that enhancement factors also there according to this equation. And equation 79, once you substitute this K s value and other what is that rate of reaction, this K r this is controlled by the mass transfer around the particles, then you can get this enhancement factor of mass transfer by this equation number 79. So, more details about this I think it will be helpful to study with these references. Here I have given some references to follow further to know more about this mass transfer here. So, it will be better to read more about this for more details of mass transfer phenomena in the gas liquid solid fluidized bed. I think in this lecture we have learned something about what would be the mass transfer rate, what would be the mass transfer coefficient, what would be the different correlations, and if is there porous or non-porous particles are there, how enhancement of the solid enhancement of the mass transfer inside the fluidized bed for gas liquid solid system we have learned. And it will be more helpful if you go through this reference more in details. So, thank you.